magnetism. All right. So our focus is going to be magnetic fields and how magnetic fields affect particles in motion. Okay. And those particles are going to be either electrons or protons. Okay. Or those particles are going to be, just electrons or protons. So that was the first one. Let me go back to that first one. Those particles are going to be electrons or protons, and they're just going to be like individual particles sort of, flying in a theoretical laboratory experiment. Okay. Versus the other type of particles that are in motion would be a current, okay, in a wire, right? And as it turns out that a wire, like a conductor, it's called, like a copper wire, if you run electricity through it, it's actually particles in motion, as we learned in grade 11 physics. And those particles are the electrons. And so basically our main focus is going to be how magnetic fields affect those two types of particles, either electrons in a wire or protons slash electrons in a sort of free flowing, or just like a free scenario where it's like they're shooting out in a laboratory type scenario. Those are your two main types of questions that you're going to be dealing with in grade 12 physics. Okay, so then let's discuss what exactly we need to learn. Okay, well, first we need to learn, what is a magnetic field? How do we make one? And what are their shapes? And then how do we kind of draw it? Okay, so we're first going to focus this first day or a day and a half or so. We're going to focus on the actual field itself. And then afterwards, we're going to talk about putting particles into those fields and seeing what happens, calculating, predicting various motions and stuff like that. All right. So this first day is just a lot of review and information from grade 11. So I'll just kind of, lightly cover this information. So natural magnetism, right? So in this section, we'll review content introduced by in grade 11 regarding natural magnetism and electromagnetism. So there's really two types of magnetism. It's natural, whereas like you've got your sort of permanent magnet, and actually this word natural is a little deceiving as well, because it doesn't. You can actually have a man-made permanent magnet. I kind of, maybe we could call this like a permanent magnetism and electromagnetism, and then even permanent is actually a misconception, because not all magnets are permanent. They're just, you could have a magnet that's considered permanent, but it's just very long lasting, right? It won't remain magnetized for, forever. It might take, a long time for it to demagnetize, but it won't, well, whatever, not forever. So we're going to first talk about the idea of a permanent magnet, which is just like a metal magnet that you would hang on your fridge. Okay. And here in this box, we explain what a permanent magnet is, or the theory behind a permanent magnet. So basically in these sort of ferromagnetic materials, they're called, you've got sort of, sections of it that are, these molecules that are sort of polarized, meaning they have sort of charges on one side, versus another side, so that they have some sort of like magnetic sense to each individual particle in the material, right? And well, if the material is just sort of randomly orientated like this, then it's not necessarily going to be magnetized. But if they happen to be all in each individual little piece happens to be magnetized in the same direction, then the overall material itself can be considered magnetized. That's what's called the domain theory of magnetism, is that each one of these little guys is like, it would be considered a little magnet in and of itself. Okay. And now, as a result, this guy would end up having like a North Pole and a South Pole, kind of like what we decided, or physics folks decided that charge should be either positive or negative. They decided that magnets should have a pole, which would be called north versus south. Okay. So we'll talk a little bit about that information. All right. Basically, what we're looking at now is the law of attraction and repulsion. So, unlike poles attract and like poles repel, very much like the law of charge, the universal law of charge. Remember that like charges attract. Excuse me. Did I say that right? No, I meant unlike charges attract, and so unlike so positive things like that. So there you have it. That's the case. Oh, here's a little quote here. It says, it may appear that a magnet will also attract a non-magnet. So, for example, your refrigerator is not a magnet, but I can all of a sudden I can put a magnet on it and it attracts the refrigerator. So how is that the case? Because what ends up happening is that magnet in that area, right? So let's say we've got a refrigerator door, right? It's here, okay, and then it's got sort of magnetic poles that are just sort of like randomly placed in its little area here, right? Now all of a sudden I approach with a magnet, and it's got a north pole and a south pole here. What's going to happen is, as I approach, each of the north poles right here are going to be unattracted or repelled, I guess is the better word, from the north poles, and all of these little south poles, right? So imagine that this here is like a little north pole, and this is a little south pole in one of these little domains we're talking about up here. Okay. So what ends up happening is each one of these little individual domains sort of orientate themselves so that all the south poles are now pointed in that direction. As I now approach with this magnet, okay, and therefore the magnet sticks onto the refrigerator, okay, and that's that. That's why. That's the explanation of this little quote right here. Where was that quote? That's this quote here. It may appear that a magnet will also attract a non-magnet, right? But in actuality, the non-magnet has become temporarily induced magnet. So, there we go. A temporarily induced magnet there. All right. Okay, the space surrounding a magnet in which its magnetic influence can be detected is referred to as its magnetic field. Okay, so the field is often detected can be detected by a small compass, which in and of itself is a magnet. Okay, and the compass aligns itself with the magnetic field on the Earth. Okay. Anyway, so that's just like a little statement talking about how a compass works. So the properties of field lines around a bar magnet here. Okay. So here we've got a bar magnet. It's labeled north, and here it's south. Basically, what's going on here is it will have its own little magnetic field. So it'll be north and south. And you're around a permanent bar magnet, the field lines run from the north towards the south. Okay. And so there's some of your rules that scientists have decided in order to delineate or write down magnetic fields, just like gravitational fields. Gravitational fields, the arrows point in the direction that the mass would be pushed. Electric fields, the arrows point in the direction that a theoretical positive particle would be pushed. And what was I going to say? A magnetic field runs from north to south. Okay. So it runs from the north, any sort of north pole to the closest south pole. Okay. That's what's going on there. All right. So, yeah, that's your properties of your fuel lines. Now, so here's a couple of fields, right, in this area. And so what we're going to do here is, is draw a diagram showing the field lines of two magnets placed horizontally on a table, right, with opposite poles adjacent to each other. So that would be this one, not this one. Okay. So if you were to answer that question, you would draw that one there. All right, so that's number one. Number two, why is it possible that nails will become slightly magnetized during the manufacturing process? Okay, this is number two. All right. Now, number two here is that what ends up happening is the nails themselves, when you manufacture these nails, they are under the influence of possibly some sort of magnetic field. So the nail, I'll draw the nail. It's like a little nail. Here you go. Here we've got ourselves a nail. If I manufacture this nail and it happens to be in some sort of magnetic field that's going right from north to south here, then what's going to happen is while this nail is sort of liquid metal, because it's being, molten metal, and then they pour it into a mold, and then it, hardens up as it cools, and you end up having a nail, and you drop it out of the mold, and then all of a sudden you're like, oh, cool, okay, I have a nail. Excuse me. If the nail happens to be orientated such that when you manufacture the nails, it's found within a magnetic field, then it will take on the characteristics of that magnetic field. Okay, and so, for example, if that's the case, then this would be a south and that would be a north pole. Okay, because magnets induce, they make other materials magnets as well. If those other materials are what is considered ferromagnetic, okay, meaning there are certain materials that can become a magnet when placed next to a magnet. There are certain materials that cannot. If I have a piece of styrofoam and I place it next to a magnet, it doesn't become a magnet. But if I have a nail and I place it next to a magnet, then it does become a magnet. Okay? If it's already a nail that's pre-made, then it'll become a magnet next to that other magnet. And then if I take the magnet away, it'll go back to non-magnetic. Whereas if I'm making a nail inside of a magnetic field, it will take on the characteristics of that magnetic field, and it will retain them because it's more of a liquidy thing, right? At that point. All right. And so that's basically what we're looking at there. Okay. Tomorrow we'll talk about magnetic fields in conductors. All right. and we'll see how that works out. Okay, magnetic fields and conductors. Make a separate video on that one.